Horsepower makes heat. This time on Engine Masters, we're gonna show you how to love that power by keeping your cool. I don't think there's anybody who knows more about torturing themselves with horsepower than I do. I mean, I could give myself a header burn from like 100 yards away. You should see some of the junk I drive. Headers right up against the floorboards, automatic transmissions blasting me with heat. I burn my feet, my toes, my hands on stuff all the time. You know how it is. Making horsepower makes heat. Strangely enough, this episode of Engine Masters is not gonna be about making horsepower at all. Instead, we're gonna talk about how to attenuate that heat problem in your car. First of all, we're gonna look at reflective heat shields. This is the type of stuff that you would put like on the underside of your floorboard or in your engine compartment to try and reflect header heat back at the engine and keep it out of the passenger compartment. So that's gonna be part one. Next, we're gonna have a look at header wraps. Do any of these super special wraps actually keep heat in the header and away from your fingers and inside your car? That will be the last thing that we figure out. What I'm gonna do first is wander into the cell and show you how we have set up my 408 LS engine and a big contraption to test all of these heat shields, which will be compared to a bare sheet of steel. Does any of this stuff actually work? We're gonna find out. Here's how we're gonna test all of these reflective heat shields. Every single one of them is stuck to a sheet of 22 gauge steel. I've got a handful of those. Now we took that sheet of steel and we've clamped it here right next to the header. We had amazing difficulty getting that to get hot, which is kind of stunning. You would think that putting a piece of steel within a 1/4 inch of a header running at wide open throttle would make heat. What we ended up having to do is a bunch of things. First of all, the engine, it's gonna be running at 5,000 RPM under a given load for 30 seconds. We had to go that hardcore to get any heat transfer. And to be honest, in your car, that could end up being worse because there's a number of things in the dyno cell that want to be working on cooling off that piece of metal. The first one was airflow. There's a lot of wind in here. And so there's cooling from convection, which is a fluid, in this case air, passing across a mass or an object and pulling the heat out of it. We had a lot of convection cooling, and so that's why we've got these blocks here that are preventing airflow across the header and across the sheet. The other thing is we wanted to make sure that we didn't have conductive heating of the sheet. Conductive is when the metal is touching the metal, and that's how the heat is being transferred. These materials are not designed for that. They're designed to prevent radiative heat radiation. They reflect heat back. And so we've got a 1/2 to a 1/4 inch gap, depending on where you look at it, between the header and the piece of steel. That way, these things can work the way they're intended to do, which is reflecting heat. Now, the other thing that was curious about all of this is what we had to learn about measuring heat. We ended up with this Fluke thermal imager. This is $24,000. The image from this is what you'll end up seeing with me and the Steves out at the table when we're talking about all of this data. It not only reads the room, but it also has specific points of temperature that we're reading. We're going to be able to read temperature right here on this header tube, and then at 2 points on our sheet that's trying to reflect the heat away. Now, the interesting thing is we learned about emissivity, which is the fact that anything that is at anything above absolute zero emits actually infrared radiation as it's sending its heat off. And that's what this measures. The problem is it can't measure something that's too shiny like a mirror. It's really technical. Bottom line, we were able to solve our technical problem with a can of barbecue spray paint. So all of these are painted black so they're not too reflective so they can actually read. The dyno is not gonna give us any data logging. We're going to be observing what's happening on the screen and letting you know what's gonna happen. Our first test is gonna be heating up a just bare sheet of steel, and then Troy will run in as we go and change from one heat shield to the other to the next, and in the end, we'll sit down, rank them from best to worst, and let you know what happened. Usually at this point in the show, I'd be having a sit-down discussion with Steve Dulcich and Steve Brule, but we decided to rip right into it. Here's what Dulcich and I are going to be looking at. That is the screen that's showing us what the infrared camera is seeing. We've got temperature points here and here on the plate, and right here you can see it on the header tube. Steve Brule's in there running the dyno test. He's going to rip this thing up to 5,000 RPM at a load that will be consistent throughout all the testing. And Dulcich, if you could please help me keep an eye on the temperatures so that we can agree on that, and I will be writing those down. We're going to start with the bare plate, and then Troy is going to go in and burn his hands and change plates out as fast as we can. Then we'll come back, and I'm going to show you all of those plates and discuss it so that the Steves will see it at the same time that you do. The first heat shield that's going to be run here is the lava shield. How's that possible?
That doesn't make any sense.
No!
It's a heat-absorbing mat.
Whoa! I have to go inspect this.
That's insane.
Is it touching? It just picked up like 100 degrees. It's 100 degrees hotter than no mat at all. Let's go look at that.
200 degrees almost.
That actually made it worse.
It made it hotter.
Now we've taken that same piece of metal that had the lava shield on it and flipped it over so that the shield is pointed out. It's not facing the header. We'll just see if there's a difference there. It's the same. That's wild. I really can't wait to run the next sheet. This one is Reflect a Cool from DEI. Another DEI product this time, but it's Reflect a Gold. It's the gold one. The next one is the Coolant Sheet from Thermotech. Our last test is going to be the only one with a little bit of insulation. It's the Sticky Shield from Heat Shield Products. All right, welcome to what we call the Engine Master's living room. We usually get to this point a little bit earlier in the show when we're all three sitting and talking. I think it's the first time that we've tested before we brought you in to talk about stuff. And man, did we test. There was a lot of stuff that just went down trying to make sure that we were nailing this test as tight as we possibly could. But we weren't able to actually nail precise degrees on this stuff, but man, were we able to see some trends that are overwhelming and really unrefutable, because we went back and forth and tested over and over and over, rebaselining, making sure that the trends were the same.
You made me do it over
and over. Hey, it's my motor running at 5,000 RPM at full load for 30 seconds over and over and over.
That's something else that we don't normally do the way we test it. I mean, I was parking the thing at 5,000 RPM, wide open, for 30 seconds at a time to make sure we were generating header heat to the point where, you know, headers were stabilizing, what did you say, somewhere around 950 or still creeping up, but kind of taking that
once we started getting in the groove, we were able to really nail a consistency where the surface temperature of the plate and the header has the same at the starting point, and you ran it at 30 seconds, and the thing ended at the same header temperature every time. So that was a lot of repeatability. It seems
well, what I saw was a lot of this is kind of like almost like when you're looking at EGTs. The way that you drive the car
makes a big difference.
Makes a big difference in how the ending EGTs are. So what I was doing was I was cruising at 2,500 for approximately 30 seconds until those two temperatures would stabilize. Being the same, you'd give me the sign of go, and then I'd run it for 30 seconds wide open.
Yeah. And so we did that a lot. I mean, we worked really hard, and we feel comfortable with our results, even if you can't nail it down to within 1 degree. You can nail it down within 10 or 20 degrees, either way, I would say. And here's the reason why we went to all that trouble, because this was a shocker. This is a product from Heat Shield Products that's called Lava Shield. It looks cool. It looks kind of like carbon fiber.
Yeah,
it's all neato. They say it's got, you know, some, I guess, basalt in it, like lava rock.
I have to say, it lends a very attractive look to the sheet metal.
It does, and it's extremely thin and light. Here's the thing that we absolutely could not believe, and we tested it 4 times, and we tested it with the lava rock facing the header and facing away from it, and every single time, it added surface temperature. To be specific, we saw surface temperatures on our 4 tests of 302, 312, and 291 degrees versus the baseline of 157 to 171. So clearly, this is doing something to retain heat and amplify it rather than shield it. Put the header here and read the temperature here, and it was hotter than a bare piece of steel. And unbelievably, we had the same problem with this product. This is made by DEI, and it's called Reflect a Gold. Once again, super thin material. Very, very thin, and obviously a gold color to it. Best run that we got out of this one was 246 degrees versus 170 at the worst for a bare piece of metal.
Still 70 degrees warmer.
How does it happen?
Heat
I don't
goes
understand.
in, but heat can't come out.
I guess it doesn't make sense to me. But we tested it over and over and over again.
It's like a nice winter blanket.
I can't explain it. Those 2 products claim to be heat reflective products, and I read the websites over and over and over and over, and they didn't do that. But then we have the DEI product called Reflect a Cool. This is the first one of our aluminized silver surface products, and it also has a little bit of thickness to it. And this reduced temperatures by neighborhood of 20 degrees.
It's pretty good.
It pulled down the temperature 20 degrees
That's
or
good.
so, so that worked. And then we had the product from Thermotech called Cool It. And this one's very similar, but it has some texture to it and probably just a hair more
Looks like a
thickness
little
to
more
it.
material.
And on average, this seemed to knock down about 25 degrees from our baseline surface temperature. So that also worked. And then the product that I looked at right out of the box, and I think you all did, and said, this is gonna be the one that absolutely works. And the reason is that it is an aluminized cover that has some bumps in it, but it has a thin layer of fiberglass insulation to it, and that insulation is gonna be the key. This is from a company called Heat Shield Products, and it's their sticky shield. This knocked 40 degrees.
Well, it's the thickest of the products. Our intuition says this looks like it should be better.
Right.
This isn't that much different than home insulation. When it's thicker, it does a better job.
I think the best insulator is air, always.
There's a lot of air pockets.
It has a lot of air pockets in it. And so really what I wanted to do here was not like a brand-to-brand shootout, but I wanted to get a variety of different styles of reflective products, and not the stuff that is sound deadener that goes on top, but the stuff that I thought you would run on the underside of your floorboards or on your inside your engine compartment under your hood. And I think my conclusion is that the stuff with insulation, with some thickness, with some fiberglass is always gonna be better than just that thin coat. This one is gonna be the one that I would pick. This is, once again, the sticky shield. On average, it would reduce roughly 39 degrees off of our testing.
That's pretty good.
That's a lot.
The other thing that I would say in all of our testing here is that we struggled to get heat into these things. And in the car, I can tell you it's way worse.
Yeah, and part of it is the length of time, I think, the duration that a piece of material is subject to the heat. Like when you've got your feet on that trans tunnel and a header's laying underneath it, and it goes on for 10 minutes, 20 minutes, a half hour, an hour, and pretty soon it's at the point where the whole floorboard is the same temperature as the collector on the header.
And when you were doing the testing, both the surface temperature of these as well as of the header was continuing to climb with time. He had it parked at 1 RPM wide open, and it just kept on going up and up and up. And you're not cruising 5,000 RPM at full load on the highway, but if you're cruising a longer duration, there's less airflow underneath the hood. And I've literally burned my sandaled feet in many, many roadkill project cars.
Yeah.
Next thing I would like to do is the age-old header wrap. I got the top 3 heat shield companies that I could tell from like shopping at Summit. The most common stuff is the Thermotech. That's their copper, Generation 2 copper. Then DEI is another big brand. This is their titanium. And finally, the Heat Shield Products Inferno exhaust wrap. So,
it's a good name.
Once again, I got these not as a shootout for these 3 brands, but because these seemed to be 3 different approaches, just sort of the old school kind, the titanium, and the copper. I don't know anything deeper about them than that, other than we're gonna find out if they work or not. I think what I actually would like to do is re-aim our camera in there and pick 3 header tubes that we're gonna wrap and get our before data.
Okay.
And then we'll run it again once we've wrapped them.
Okay.
So let's re-aim and get a baseline. We did this test once on Engine Masters where we used header wrap to find out if the wraps make horsepower, because a lot of the wrap companies claim that that's true. We were not able to duplicate that scenario. They say that by wrapping the pipes, it makes it hotter inside the pipe, which makes higher pressure, which makes it escape out the back faster, which, you know, pulls, what's the word? It like evacuates the exhaust better and makes horsepower. We were unable to prove that. That's not what we're doing this time. This time we're just trying to look at the surface temperature. All right, rather than clamping it, Steve's gone with the half hitch. I will cut off the excess, and then you've proven your abilities. You can do the other 2 as well.
I knew that was coming.
Yeah, I know.
But I'm enjoying wrapping headers so much, I'm looking forward to doing the rest of them.
Normally I would get a wider material for wrapping header tubes, but this is what was available, so I got 1 inch on all of them. He's doing about a half overlap on each wrap, like so. Does it seem to you that the titanium wrap is a little bit more flexible, sort of like softer, fabricier?
It just has some very endearing properties. You may be right about that.
Yeah, it seems just softer. It looks cool. It's like semi-metallic.
Yeah, the question is, how's it gonna do as far as the heat handling properties?
I think these are all gonna work. You're doing impressive work, Dolchek.
When it comes to working with fabric, I'm your guy.
We've been through a lot of heat shield products on our LS engine. Now we're doing header wraps. Steve just wrapped 3 different brands on 3 different tubes, and we know that we had 1,000 degrees or 950 to 1,000 degrees in those tubes before, and now Brulee's gonna test it and see what kind of temps we see after the header wraps. All right, he's gonna give it a full 30 seconds at wide open throttle at 180 RPM.
It's cooler.
Yeah, looks to me like it knocks a couple hundred degrees out of it, anywhere from 150 to 200 degrees. This is actually gonna be pretty good. I like these results. The thing is, I'm gonna alert the audience to the fact that you can't really expect any 2 header tubes to be identical in temperature to begin with.
No.
Because of cylinder-to-cylinder distribution and coolant layouts in the cylinder head for a number of reasons. But I can tell you that all of these wraps knocked heat out of the surface temperature, which is good. So our very first one on this cylinder was the Heat Shield Products, and it knocked out 168 degrees. And then we had the DEI titanium wrap, and that one knocked out 106 degrees. And finally, the copper one, which, by the way, there's a ton of copper dust in this stuff, it knocked down 162 degrees.
Wow.
Yeah, so if you just look at the raw numbers, we've really killed 160-something degrees out of both of them, and the titanium was only 105.9. I can't say that's really a difference in the product. I mean, it's notable, but it could just be differences in the way that header tube's making heat. I don't know.
I'm impressed that they work that it knocks that much temperature out in general.
Yeah.
And the thing I'm even more impressed with is how well the two of you guys can actually wrap header tubes, because I suck at it. I suck at it.
I use hose clamps because I won't deal with those little tiny stainless clamps or anything. He just tied it on there like a mariner. You should have seen him.
Like a mariner. Thanks, Freiberger.
I figured you would like that.
Yeah, I did like that a lot.
Yeah, you were the captain. You were the pirate of exhaust wrap.
Matey.
Yeah.
He told you that's what he was going to do.
He said, I'll wrap it up right now, matey. Anyway, I think we learned a lot on this episode. We went through a lot of different heat shielding products, and mind-blowing to me. I still can't fathom it. We tested it over and over and over again to make sure that we were correct. 4 times we had products that raised the surface temperature above what we saw with a bare piece of metal. That was the standout crazy thing to me in the episode.
Yeah.
I did also learn that if I'm gonna deal with a heat shield product, I'm gonna use the one that has a little bit of insulation in it. I think ultimately air is the best insulator.
Yeah, I mean, it is a little more fragile. You have to be more careful putting it in to make sure that it doesn't get torn or something. But if you're careful, and once it's in, it obviously added the best insulation.
Yeah, undercarpet or something, that is going to be the best stuff. And then the last thing we did, of course, was the header wraps. I expected them to work. They all did.
Yeah.
And so I'd say performed as expected. You know what, though?
What?
I'm solidly ready to get back to actual data instead of observations and actual horsepower instead of just heat.
I kind of felt left out this episode. I mean, I was blocked. I couldn't see the header. I couldn't even participate because I couldn't see it. Yeah. And I had no numbers to share with you. So it was just...
yeah, you were just sitting there pulling the handle.
Yeah.
Now, we'll let you do more next time, I promise, as we make more horsepower, which is what we really prefer to do every single time on Engine Masters.
I'm enjoying wrapping headers so much, I look forward to doing the rest of them.
Just don't sever an artery.
Yeah.
There we go.
If I severed an artery, would you get the other 2?
We might wrap for the day.
Okay.
You getting fiberglass in your fingers?
No. No, I'm being very cautious not to get fiberglass in my fingers.
Are you getting titanium on your fingers now?
My fingers are already titanium, bro.
Is your oxygen sensor lying to you about your air-fuel ratio? That's what we're gonna find out this time on Engine Masters. Modern wideband oxygen sensors have absolutely changed the motorhead world. You just take this doohickey, screw it into your exhaust pipe, and through a bunch of technology and electronic extrapolations, you can know exactly what the air-fuel ratio is that's being consumed by your engine. And through that, it has enabled all sorts of magic with electronic fuel injection. And for carburetor guys, all of a sudden, you can buy a gauge that you can put on your dash and know exactly your air-fuel ratio and all sorts of different driving conditions so you can tune the thing to perfection. Now, because these things are so magical, I started researching them, and it got super technical, and ultimately I came down to one question. Can I actually trust this thing? Why would I ask that? Well, because the aftermarket has a lot of different ways to install an air fuel meter in your car. So what you're gonna see here is 2 segments. First, we're gonna look at aftermarket gauges intended for carburetor guys to put on the dash to read out an air fuel ratio so that you can tune your carburetor. Second, we're gonna have a look at the sensors themselves and how the readings from them might be altered by the installation of the sensor. And that's gonna apply to everybody, from carburetor guys to people who are trying to tune with EFI. It's gonna end up being a really fascinating episode. Let me tell you about part 1 and the gauges that we're gonna be testing. I went to Summit Racing and I bought 5 different gauges that you can put in your dash. I've got here a digital autometer. This one is from NTK, the highest end unit that I've got here on the board. There's an analog version of the autometer, an actual needle to tell your air fuel ratio. Then I've got one from AEM and another one from Innovate Motorsports. These are all wideband sensors. There's nothing here like the early days where you had the rich lean indicator that we saw in like the mid-90s. All of that stuff was bogus. We're gonna find out, do all of these gauges agree with each other when you plug them all into the same pipe and ask them to tell you the air-fuel ratio? And so everything you'll hear us discussing in the episode is presuming that you're running gasoline. Now that you know that you're gonna be reading an air-fuel ratio number, let me just briefly touch on what that actually means. It is literally what it says. It is the ratio of air to fuel being consumed by the engine. So a leaner mixture, meaning less fuel, is a higher number. 14-to-1 is leaner than 9-to-1, which is a richer mixture, which means less air per unit of fuel. So once again, higher number, leaner, less fuel. Lower number, richer, more fuel. The numbers that we will advise you on air-fuel ratio tuning tips will be different if you've got E85 or anything like that. So just know that going in. That'll be the story about the gauges. The other thing that we're gonna do is test these sensors in multiple locations in the exhaust pipe. We're gonna do things like unplug a spark plug wire and see how that affects the readout versus the reality of what your engine is doing. We're gonna do all of this with a Ford crate engine, an old Ford Motorsports 514. We got a little bit of a camshaft in it. It makes about 640 horsepower and 640 pound-feet, but that's not important right now. Believe it or not, this is an episode of Engine Masters that does not address horsepower. All we need this thing to do is pump smog so that we can test all of these gauges and sensors. All right, I'm gonna roll all of this stuff into the dyno cell. Troy Goldie here at West Tech set up this whole like custom dash for us so that we can read all the gauges at the same time, get them all wired up at the same time, and I'm gonna show you how we did all the sensors at the same time. And once I've shown you that, I'll sit down with the Steves and we're gonna start making some smoke. Now we've got all this stuff set up inside the dyno cell and we have them all powered up. All of the instructions that I read for these things say that one of the most critical things about them is the 12-volt power supply and ground for accuracy, and so these are all going to be the same. Now, if you look at them closely, you can see every single one of them is displaying an error mode right now, and that's because I haven't installed the sensor yet. Each of these gauges uses a Bosch-type oxygen sensor with the exception of the NTK, which uses, unsurprisingly, an NTK sensor. Now let's talk about how we're going to mount our oxygen sensors in the tube, because when you get one of these kits, you're gonna get a bung and have to weld the sensor into a tube somewhere. We have 10 O2 sensor bungs going on right here. 5 of them are plugged. They're in various locations. All of these are going to read the same. But if you're doing it in a car, all of the manufacturers agree you cannot put the sensor on the underside of the tube or at an angle like this at all. And the reason is that muffler water that you get in the morning, that condensation is going to collect inside the sensor. And they all say, if you heat the sensor up or if you fire the engine up while it's powered up and you've got that water in there, you can thermally shock the sensor and trash the thing. So you want to put the thing not quite 90 degrees, but above so that it drains, or put it around all on the top. We haven't completely done that, but that's critical for your installation. Now I'm going to start installing sensors here, and after that's done, we'll get to running this thing. I'm super curious about this because just recently, Dulcich and I had a situation with 2 gauges in one car giving us radically different opinions.
Confucius say man with too many watches never knows what time it is.
There you go. That's what this is. You know what I wanted to ask you guys, I mean, for the audience's benefit, and maybe you'll educate me as well, is let's talk about what people are even looking for on an air-fuel gauge. Like naturally aspirated engine, where do they want to be at idle, at cruise, and at wide open? Sort of guideline.
Depends on the engine, right?
I think idle is honestly the biggest question mark there, because some things like the idle way rich and other things don't. And we know like our 871 supercharged deal wants to be way richer at idle so it doesn't surge.
I mean, I think you can get a normally aspirated engine into the 13s, low 13s at cruise and at idle and keep it pretty clean. But you will find with larger camshafts, they take a lot of fuel. That's that stinky smell. And so it actually is going to read richer at idle than maybe is desirable, but that's what it takes because of the overlap.
Idle really depends on the camshaft and other factors, but it really is what your engine wants. Cruise, I've cruised stuff at 14.5 carbureted and been perfectly fine with it as long as the power valve or the EFI is enriching right away. And then steady state wide open throttle, like going down a drag strip,
12 to 13.
Now we're gonna see if these gauges that you can use at home actually agree with each other. We'll move our camera around and focus right on the gauges so that we can see what's going on when our big block Ford is running. And next time you see Steve Brule, we will have data on whether all of these things agree with each other or not. That was hard to keep track of.
Yeah, it was.
That's an eye teaser. Let me know if you guys agree with this methodology. I think we'll play it back and I'll just call out and have them pause it maybe 5 times throughout the run.
Every couple of seconds, because the run would last 9 seconds.
Okay.
In the range that we did it in, so.
And then I'll write the data down, and we won't average them because at any given RPM point, the air-fuel ratio is gonna be different, but we can look across the chart and we can see, is there one that's consistently the leanest?
We're looking for trends.
Trending, yeah. Okay. So let's play it for like 1 second and then pause. Pause. Okay. All right, we just went through and collected all of the data at 1, 2, 3, 4, 5, 6, 7 points during our poll, and I looked at each data point every time we paused the video, and I wrote all the way across what the air-fuel ratios were. We circled all of the leanest ones, which would be the highest number, and we put an underline under the richest ones, which would be the lowest number. And consistently, the AEM is reading the leanest. As far as richest, it's both of the autometers.
Yeah.
One of the autometers reads analog and the other reads digital, but I'm going to assume that the gauge and the processor and everything like that are the same. So that makes sense that the 2 autometers would essentially be a tie for richest. But let's talk what the scale of richest to leanest is.
When I was reading those to you, it was the 2 on the left appeared to be the leanest consistently, and the 2 autometers were pretty much dead on within like a tenth
of each other.
Of each other, yes.
Yeah, they definitely are.
And that's good.
Yep. So what is the scale of richest to leanest? For example, if the richest one, the autometers are reading 12.0, the AEM is telling us 12.6. 12.7 to 13, basically. 12.5 to 12.75. So the variance seems to be 1/4 to 1/2 a ratio.
Yeah. And, you know, this is completely subjective, but the way the board was set up is I can see this autometer gauge. I couldn't see the other ones. And this autometer and our gauge were reading, I mean, what I perceive to be basically the same number within a tenth or 2, and that's close.
I don't feel comfortable, therefore, saying the autometers are right and the others are wrong. That's the thing we can't do here, is actually identify which one of these is right. We don't know. There's no way to know without probably some incredibly huge and expensive scientific equipment that no dyno shop has.
What I would say is I'm comfortable with any one of these within a 1/2 a ratio. I mean, that's tolerable because any one of these is going to keep you out of trouble.
And to your point, it's like that we can tune stuff on the dyno and change a ratio by 1/2 a ratio and do nothing in most cases.
Or you're tuning the thing and you want it to be leaner on cruise than a wide open, and you're using it as a tool, and you can see variations as you're tuning, and whatever your progress is, what direction you're going.
I totally agree with that, and my conclusion to this whole thing is they're way better than we thought they were going to be. They don't exactly agree with each other, but the range of disagreement is not the point at which you're gonna get yourself in trouble tuning your engine and hurting your engine. And we all feel, as Dulcich pointed out, that once you know your gauge and you know how your car performs, you've got a scale of rich to lean and you're in good shape. So we're happier than we expected to be with all these different gauges. The next thing we're gonna do is go show you some differences that you can get in your readout. Maybe, we'll find out, based on the sensor itself. Now we're going to be using Westech's Dyno's oxygen sensor reader. But what I want to do is take the sensor and move it around and show you like how the readouts might change depending on how you install it. So first, we're gonna run the sensor all the way back here where we were testing earlier today. We'll get a baseline. Then, second one, I'm gonna move it up to the middle position. And then the last one, I'm gonna go move it into one of the individual header tubes. So this is the curve when we had the sensor kind of further back than we normally would, right? Where we had it earlier in the show. Let's have a look at that versus the sensor that is in the header collector right where 4 tubes come together. Same thing. And I know it looks kind of wild. That's because the carbureted engine will kind of do this. It's not a hyper-tuned EFI setup. And so you do see the air-fuel ratio go from 12.5 to 1 lean, all the way down to 11.6 to 1 rich, and all the way back up. But you'll notice it tracks the same with both sensors, except for this area right here, which is the difference of...
tenth and a half,
which is kind of irrelevant. Basically, we're looking at the same shape. My conclusion is that the distance between here and here does not affect the way the sensor reads.
No, I think maybe that distance has more to do with keeping the sensor dry than how accurate it might be.
The next one, though, is a sensor that's in 1 header tube. It's reading 1 cylinder, not all 4. That's gotta be different. Yeah, different. So the red line here is the air-fuel ratio just in that 1 cylinder, and it's a difference now of 1.2 of a ratio. And if you've seen a lot of episodes of Engine Masters, we often discuss cylinder-to-cylinder distribution, which means you could have 1 cylinder that's really lean and 1 that's really rich, and they average out and give you the number that you read on your O2 sensor.
Yeah.
The lesson there, to me, is in a hot rod application, just stab the thing somewhere between the collector and the end of the transmission, wherever fits conveniently on the car.
You just sometimes don't have options. You just go to the spot where it fits.
I think the next thing that I want to do is simulate a big exhaust leak ahead of the sensor and see how that's gonna affect it.
Sure.
So will a leak contaminate your reading? I'm gonna go move that plug around. We'll pull this plug out, leave that open, and then move the sensor back to here. That should suck in enough air to make a big difference. We're gonna run it with the hole wide open. We just did the test with the plug removed, so we had a massive exhaust leak. And in theory, when you do that, it'll suck some fresh air into that and lean out the reading, right?
Yeah,
right.
It sees more air.
It's straight up, yeah, fresh air means it reads leaner, and we saw that exactly. We actually have the dyno data on what it looks like on a full dyno pull. Let's look at those two. Here are 2 plots for the air leak versus no air leak on a full dyno pull. The black one would be normal, no air leak. The red one, sure enough, it's a leaner because we had air introduced into the system.
Well, interesting to me is it didn't lean out less as the RPMs rose. It seemed like it was a constant all the way across.
Basically, I think what's happening is that there's enough exhaust pressure that it's pushing exhaust out that hole rather than pulling oxygen in.
I think you're exactly right. Instead of siphoning it in and mixing it over the sensor, it's actually created a whole high pressure area where it's actually a leak now.
The interesting thing is that's a pretty big hole.
Yeah.
Bigger than any exhaust leak that even I can make. And it didn't make that radical of a difference. It's from 12.5 to about 12.9 to 1 or something like that. So that's a little bit intuitive with the air leak. The thing I really want to see is unplugging a spark plug wire. You know that if you unplug a wire, there's going to be raw fuel pumped into the exhaust. Does that make it run rich because there's more fuel in the exhaust? Or does that make it run lean? And by say run lean, what I really mean is read lean.
Yeah.
Now we've run our tests with 1 spark plug wire removed. It's running on 7 cylinders, and when that happened, the idle got just a little bit leaner. The part throttle cruise got 2 full ratios leaner, and look at this on a full dyno pull. The black line is richer, and that's on 8 cylinders, and the red line is on 7 cylinders. So Why would raw fuel pumping in the exhaust make the engine run leaner?
It's pumping more air.
It's sensing leaner.
Yes.
It's reading the gauge leaner.
Yeah. I've seen applications where there's black smoke puffing out the exhaust and the gauge reads a ratio or two leaner. It's because it's unburned fuel, and that's the black, but there's a lot of air there that goes along with it too because it wasn't supported by the fuel and there was no combustion. So now it's pumping air and running raw fuel in a hot pipe. So it's very counterintuitive. A lot of guys...
Yeah, because the oxygen sensor, it doesn't see fuel. It sees air or oxygen, so...
That's probably one of the best lessons in the episode, is if you have a dead cylinder, your gauge will read lean when in fact you have a different problem. Now I want to go to probably the most common thing that we see on race cars with O2 sensors, which is putting it too close to the end of the exhaust system. And to show you what happens there, I'm gonna go have Troy remove a muffler off the back of it, and we'll do our very last test. Now we've got the muffler removed, and the reason is you get some backflow, some air getting sucked in that'll affect the O2 sensor reading. Watch. The episode just keeps getting more and more interesting. We just saw a reading of 23-1. I didn't think that your gauge would even go that lean.
Well, that's basically what the engine's shut off. It reads 23-1.
Right. So it just, at idle, the data is worthless. Worthless with the sensor that far from the end of the exhaust system. At cruise, it was about 1 point leaner than it would have been otherwise. But show us what happened at a full wide open dyno run. The black lines here are set up normally. The red lines are with no muffler at all, and look how much leaner it is at low engine speed when you've got that sensor open to the wind. And then it actually narrows up because...
This just seems to be mass flow. The more flow there is, the less difference it makes.
Yeah, the more blow, the less suck.
Right. It's
all
just,
the exhaust is going that way.
And no air has much time to get back in or opportunity. So by the time you get to the top of the curve, that sensor could be way up the pipe and it's the same thing.
And just to send all of this home once again, remember, the engine is not actually running leaner. It is only what the gauge is reading. And that's really what we've anchored this entire episode on. And I would say the conclusions are clear. First of all, those aftermarket gauges, the 5 that we tested anyway, are all pretty good. Yeah. And second of all, the sensor location thing, obviously it was different when it was in the primary tube, but when it was this far apart in the exhaust system, that didn't matter. We think the sensor location has a lot more to do with not getting condensation in it. After that, we tried the hole. And that didn't really make as much difference as I thought. It was half a ratio as far as what it read. It made a way bigger difference when the sensor was too close to the end of the exhaust system. And then the real clincher is we pulled a spark plug wire and learned that when you dump more raw fuel into an exhaust system, a gauge will read leaner. That's a lot of stuff.
Yeah, well, when you were dumping the raw fuel, you were just pumping a lot of air that wasn't burned. So that's what the gauge was really seeing, was all that unused air.
But your eyeball would see black smoke.
And so counterintuitive, I love it. It just worked perfect.
That, for a fairly simple episode, draws a lot of really interesting conclusions for me. And even this weird stuff like testing the holes, it gives you knowledge that you can use in the real world when someone's having a problem.
Or help you identify a problem that you didn't even know you had.
Yeah, I have a lot of problems I don't even know that I have. And we'll discover more and more of them as we continue on the show that we call Engine Masters. Nitrous oxide, we're gonna turn 570 horsepower into 780. But sometimes you gotta control the violence. And that's what you're gonna see this time on Engine Masters. My personal long-held belief is that nearly any V8 can and should accept a 200 horsepower shot of nitrous oxide. And on this episode, we're gonna talk through how to make that safe I've actually done way worse, trust me. And we're also gonna tell you how to control that hit a little bit for extra traction at the drag strip and for extra safety on engine parts and drivetrain parts. It's all about what I call the hit. What happens when you stab the button? How violent is that nitrous gonna hit? We're gonna do that in a couple of interesting ways. First of all, just with something as simple as changing the length of some hoses, and with something a little bit more high-tech using an NOS mini 2-stage progressive nitrous controller. So that's kind of the super low-tech and the high-tech, but super simple. Wait for it, it's gonna be cool. But man, right now I wanna tell you all about the horsepower that we're gonna be making, because this I love. We're gonna take 570 horsepower and turn it into 780 before we're done for the day. The engine we're starting with is my own GM LS-based V8. It started life as a 6-liter. It's now 408 cubic inches. It's meant to be a power outer engine, so it only has 9.3 to 1 compression. It has rings that are gapped for nitrous. It's all forged. It's got blueprint engine cylinder heads. The camshaft is a real tame average cruising LS type deal. The duration at 50 thousandths tappet lift is 225 on the intake, 238 on the exhaust. The intake manifold that we're gonna be using is carbureted this time. We're using the GM version of a single plane intake manifold, and the carburetor is gonna be a Holley XP at 750 CFM. Now for the nitrous system, it's sort of a Frankenstein of stuff. We've got an NOS bottle, a Dash 4 feed line. We're gonna use NOS cheater solenoids. It's got a Wilson bracket that's actually pretty cool. And we've got a Zex perimeter nitrous plate under the carburetor. Just as a refresher course really quickly on how this is gonna work, nitrous oxide is stored as a liquid inside the bottle, and it travels through the hose up to that solenoid. On the other side, you got a solenoid that is controlling gasoline. The gasoline and nitrous are both introduced to the engine at the same time. The nitrous freezes the intake charge, which makes power. It also carries oxygen with it. The molecule of the nitrous oxide breaks into oxygen under temperature and pressure in the cylinder, and extra oxygen means that you can burn more fuel, and that's burning the extra fuel and that coldness that makes a whole lot more power. Now, the thing is, when you open these solenoids, you've got nitrous and fuel going in at the same time. The nitrous is at about 950 PSI, and the fuel in a carbureted situation is about 5 to 7 PSI. The thing that can happen is the nitrous gets into the engine first. It spikes a little bit lean before the fuel gets into the cylinders, and what you see on a dyno chart is often a big spike in power. Like you'll hit the button, and boom, the power goes straight north, and that can be violent on engines, and that can break traction, and that's the thing I call the hit. That's what we're gonna try and control here. Now, I actually kind of dig it. I want to go wide open all the time, every time. Brule doesn't like it quite so much, and so what he heard from a lot of nitrous tuners is that you can affect that hit simply by changing the length of the hose that runs from the nitrous solenoid to the plate underneath the carburetor. Once again, that nitrous is at 950 PSI, so it's traveling that distance like stat. If you put a longer hose on it, does it slow that down so that the fuel has a greater opportunity to get in the manifold along with the nitrous oxide so you don't see that big hit? Well, we've heard that a lot, and we're gonna test it. We're gonna use an 8-inch hose, a 36er, and believe it or not, we also have a 5-foot-long nitrous discharge hose. Nobody actually does that, so if it doesn't make a difference, nothing will. Here's something that will guaranteed make a difference. That is the NOS Mini 2-stage progressive nitrous controller. What this thing does is allows you to go on a touch screen, and you can change that hit at the press of a stylus on your screen. For example, instead of just hitting a button and having 100% nitrous flow, you can start at 25% and ramp it up to 100% over any period of time you want. 1 second, 2, 3, 4, and we're gonna see how that affects the power curve on the dyno as well. All right, we're gonna go load this thing so that we can start making noise, and we're gonna start right away with a nitrous hit, a 200 shot with the 8-inch hose. I'm gonna sit down and talk to the Steves about all of this stuff, and by the end of the day, I think we're gonna have my LS running better than ever and ready to install on a car. We're gonna be running a lot of nitrous oxide through this thing today, so I think one of our first topics should be safety. What do you have for a tune-up?
Actually, I do have a pretty conservative tune-up, and it's basically, it's considered a 175 shot, but it actually makes closer to 200 is my guess. from just past experience. It's basically gasoline jet in the 60s and a nitrous jet in the early 70s. And I've actually got 13 degrees out of it currently.
He doesn't want to say, run 26 degrees of timing. Because your LS might not say the same thing depending on what computer you're using or how you're measuring. So we talked about the jetting that you've got in the thing, about a 200 shot with about a 73 nitrous jet, 72. And then we talked about ignition timing. We should talk about the fuel.
Sunoco.
Sunoco, what?
116.
Okay, so big, heavy, high-octane race gas.
Detonation is a death sentence. It's as simple as that. So we just cannot let it detonate, hence the high-octane fuel and the excessive, I'll say, by this much retard in the timing.
Just for safety.
Yes.
Yep, and making sure the thing doesn't run lean. And, of course, we've got a killer fuel system. It's all aeromotive stuff, I believe, on the dyno, so that's never going to be a risk. And the engine itself has low compression. It's only 9.3 to 1. And really, compression ratio is something that isn't discussed a lot as far as nitrous hits, but I think the lower your compression, the more added nitrous oxide horsepower you can have and still be safe, just because the cylinder pressures are lower. And the last safety thing that this reminds me of also is the RPM at which we're engaging the nitrous oxide. Why wouldn't you hit the nitrous at 1,500 RPM?
Because a 200 horse nitrous system is still 200 horse.
No matter what RPM you hit it at. And so therefore you do the math backwards on what the torque is.
At low RPM, cylinder pressure has to be way higher for a given horsepower gain. So
there you go. I think we just start straight with the nitrous.
I say yes.
All right, first test, what are we doing? And what I really want to know is what you're gonna use for a hit RPM.
Well, you're not letting me push the button as normal. You want it to be a little more accurate than that. But we're actually using the NOS Nitrous controller as a window switch at this point. It still has 100% activation as far as the solenoid is concerned. But we're activating it at 4,800 RPM. I figure it'll take to about 5,500 to ramp fully in. And I'd like to carry the nitrous for about 1,000 RPM. So it will end at 6,500. And the shortest and first hose we're going to start with is an 8-inch long hose from the nitrous solenoid to the plate.
Which is like factory. It's like what a kit comes with. It's the shortest one. Okay. All right, 4,800 RPM, which even though the controller's at 100%, you think's not going to fully have all the air out of the lines and everything and not have the fuel hit the cylinder.
No, we've seen this before. It's not a vertical line. It still has to ramp in some. And as it accelerates the dyno, it's almost like a torque converter, you know, drives through it a little bit. And so I'm seeing about a 500 RPM move typically.
All right, well, we'll watch all of that. Okay. Cool, fire it up. Brulé is ready. He's got his finger on the button. His button is triggering the window switch in the NOS controller. And pretty soon you're gonna see our LS run on its first shot with the original hose, 8 inches.
8 inch.
We got that. Now we're gonna see what happens with longer hose lengths. We've got a 36 and a 60. We're gonna go change them both up and come back and show you what happened. The only change we've made now is the length of the hose. We've got a fresh bottle, same amount of nitrous in it, exact same temperature. We're gonna see what happens. In comes the 60. Here's our hit with an 8-inch hose. I'll give you the peak numbers, but the peak numbers are not the story in this episode at all. When we had the 8-inch hose between the solenoid and the plate, we saw 729 pound-feet of torque and 766.4 horsepower. Now look what happens when we go with the 36-inch hose. And remember, the theory we were looking at here is that the longer the hose, the softer the hit on the nitrous. This tells you that that's not true. The black lines here are with the 8-inch hose, and the red lines are with the 36-inch hose. And you can see that when the nitrous is activated here, it tracks exactly the same. And then, in fact, the longer hose ends up hitting a little bit harder.
Yeah. And sooner.
Sooner. Yeah, you're right. Sooner and harder later on. And actually, there's a little bit of a horsepower difference at the top, too, which we'll explain. Now let's look at the 60-inch hose, 5 feet long. Same story,
yeah,
basically.
Basically, it's a 36.
Okay, and look at this. This is the 60-inch hose in red. So the longest hose that theoretically should create the softest hit is actually giving an even harder hit. So does that mean that the inverse is true, that longer hoses hit harder? No. What it actually means is that it's really, really hard to get consistent with the nitrous systems on any of this stuff. So you guys are comfortable going, at minimum, in this test on this day, hose length is not a tuning tool. There's no consistent trend that says that it either hits better or hits worse.
No.
Does not matter, which makes sense to us because remember we were talking about once the solenoid opens.
It doesn't exist anymore as far as the track's concerned, from the bottle to the engine.
Right.
So when you're adding a few feet of hose here compared to 20 feet from the bottle to the solenoid, what percentage change? And then how fast does liquid nitrous go down that little tiny hose?
It doesn't care.
I think a whole lot of it has to do is if the nitrous bottle had 5 pounds in it, this might make a big difference. With 950 pounds in it, it's happening so fast, it doesn't see that distance.
Which brings us to the next part of the story, which is the real thing that we struggled with here, is that the variance in all these horsepower numbers right here and in how it hit really comes down to the volume of nitrous in the bottle, the size of the nitrous bottle, and the temperature of the nitrous bottle. And so our conclusion on this part of the test, again, is hose length is not a tuning tool, especially at this power level, and the bottle temperature and pressure is huge, and that's gonna translate to every power level.
Yes.
As a matter of fact, it's gonna get more radical.
Yep.
You're not gonna be happy unless I show you what this engine makes as a baseline without nitrous oxide. That's the red lines here. We're making 512.1 pound-feet of torque at 5,400 RPM, and it makes 569.4 horsepower at 6,500 RPM. And on this nitrous pull, the torque was 729.9 versus a horsepower of 766.4. So we are seeing a nitrous power gain of 197 horsepower.
Okay.
I call that 200.
Me too.
Yeah, because sometimes it gives you 210 and sometimes it gives you 190. It just depends on what mood the bottle is in at that particular moment. All right, let's go in the dyno cell and show you what's gonna happen next when we install the NOS Progressive Nitrous Controller. We got nitrous oxide on my 408 LS, and we've been testing, trying to tune the way it hits when you stab the nitrous button by using different length hoses. That was a dead end. We saw nothing earlier in the episode on that. I guarantee what we're about to do will work. We've installed this doohickey, which is an NOS mini 2-stage progressive nitrous controller. What this does is it's gonna allow us not just to hit a nitrous button and have all the nitrous flowing at the same time, it's gonna allow us to decide how much nitrous we wanna start flowing right when we hit the button, and we get to pick a time frame at which it'll flow 100% nitrous. So we can go from 25% to 100% over 1 second, 2 seconds, 3 seconds, whatever we want. Let me show you how we're gonna set this up on our little handheld device here. So I'm gonna start at 25% nitrous flow. If it's a 200 horsepower kit, this means I'm gonna start as a 50 horsepower kit, and it's gonna ramp up to 100% or 200 horsepower over 4 seconds. And now, because I'm now flowing much less nitrous at the hit, only 25% of it, I can start it at a lower RPM. Before, we were activating it at 4,800 RPM because we didn't want to hit 200 horsepower lower than that. But now, I am actually gonna start flowing my nitrous at 3,500. It's starting at 3,510. It'll end at 8,000. We'll actually shut it off manually before that. Let me check my ramp builder. Yes, it saved my data. All right, that's starting at 25%. We'll see what that does, but I think I'm gonna come in here and probably change it up a few times and see what happens. But here's our first setup. We saw what happens at 25% at the start. I'm gonna change to 5% and see if that softens it up at all. Now, Brulé and I were talking about whether or not 50% duty cycle on the solenoid means 50% horsepower. So what I'm gonna do here is make it so that it starts at 50% and ends at 50%, and we'll see what kind of power we make. We're back from looking at everything with our little handheld controller. I ended up not just doing one program in it, we ended up doing several things. We're gonna start looking here at our power number that we ran last time. This is the one with the 60-inch hose. We have only got the horsepower plot shown on here. Normally we do horsepower and torque. It's gonna be easier to look at with just horsepower because we're gonna show you what happened when I set up the controller in its initial configuration to start flowing at 25% and then go all the way to 100% over 4.5 seconds. And there's the difference. In red, this is the controller in action, and in black, that is Steve Brulé stabbing the button. Although we did have the window switch activating it up at 4,500 RPM there as well. So what we can see here is not 100% what I was hoping for. I thought that it would end up sloping a little bit more gradually, when in fact, setting it at 25% makes it hit pretty hard down here. The slope of this curve with the controller and this curve without the controller is a little shallower, but not as much as I thought.
You know, I think the advantage to the controller is if you don't like that curve, you can go put a smaller percentage in and you can soften it up and slow it down.
Yeah. You can. One of the things you can do actually is, I showed you the screen on camera that shows just go from 25% to 100%. Well, once you do that, the handheld will also make a graph with plot points on it. And let's say you're working at the dyno and you see this and you're like, ooh, this is a little meaty in here. I don't want that much torque gain at that low of an RPM. You can grab the points almost like a timing curve graph and pull it down and shape it to what you want. Now, the other elephant in the room here is that with the controller, we made 783.7 horsepower, which is super cool. That's a big gain over our baseline. But the reason for it is, once again, remember when we were talking about hoses, our big wild card was volume and temperature of the bottle. That was a brand new, fresh bottle, very first hit. Every time we hit a first hit, we would see 780 horsepower. But then, you know, we were fiddling with it quite a lot this time, and we ran it like 5, 6, 7 times in a row, messing with things, and it made about the same 740 to 750 over and over and over and over.
It seems that once the initial head is off the bottle, depending on the volume, it will maintain that pressure for a long period of time.
Let's show when I pulled it down to have 5% at the initial hit, ramping up to 100% over 4.5 seconds. Once again, we were just talking about how we made a bunch of runs and had lower bottle pressure. That's what you're seeing here. That's why the overall power is lower, but you can also see how it's affecting the shape of the hit, both with the lower bottle pressure and with the less aggressive attack on the NOS progressive controller. Another thing that I did, which was to start at 50% and end at 50%, meaning instead of jetting the nitrous system, I was like, I just want to run less power today because I don't want the track to throw me out for being too fast. And boom, right here in the red line is starting at 50% and ending at 50%. So you can see that it ended up with much less power than we've had on any of our runs. But because it was 50% to start, it hit harder.
Yeah.
So the blue line here is 25% to start, and the red line is 50% to start. And so you can see the difference in the attack right there. And that's actually with the blue having really high bottle pressure and the red being low. So that tells you that you can really make a difference with that controller.
What it shows me is you can kind of do whatever you need to do.
Yeah. Okay, it's time to sort of sum it all up. I think the big aha moment in the episode was everything that you've told me for years, that you've heard for years about nitrous hose length, softening the blow on a plate system.
I was wrong.
It just didn't seem to be there, at least not on this test at this power level. It didn't seem to make a bit of difference. And then on the progressive controller, it ends up being more tunable than I thought, but probably needing more tuning than I thought. Just in the sense that I thought that this would be much more linear, and I realized, no, you probably have to go in there and mess with it just a little bit, but it's super cool.
It is, absolutely.
Yep, and it'll do it for 2 systems, and it'll also, you know, slice and dice your giblets and whatever you want. It has a bunch of other features.
The magic of electronics.
The second big takeaway, as you can see by how those power numbers vary so much at the top of the chart, is you really need to pay attention to your nitrous bottle volume and pressure if you want to be consistent with nitrous.
I think I need nitrous now.
I think you absolutely do, and I know exactly what I want to do with nitrous, which is coming up on my 582, probably the very next time that we all get together to shoot Engine Masters. About a year ago, we turned the guts of this thing to shrapnel, but my 582 big block Chevy is back and reconfigured. I'm gonna find out for the first time how much power it makes, and we're gonna do a showdown of big hankin' race carburetors. My 582 cubic inch big block Chevy is back. This is the same engine that made 1,000 horsepower naturally aspirated on prior episodes of Engine Masters. Unfortunately, we went to test it one time and the head broke off an intake valve and it turned the entire bottom end into gravel. No good at all, but it's back. It's fresh, it has a new configuration, and on this episode, I'm gonna find out how much power this new setup makes for the very first time. We're also gonna do a shootout of big race carburetors. We're gonna do 1,050 CFM versus 1,250 versus 1,450. Now, we've done this on smaller engines with smaller carburetors, and I can tell you that if you're dealing with like 350 horsepower or less, you want a 600 CFM carburetor. And if you're dealing with, say, up to maybe just the underside of 500 horsepower, a 750 works. Above that, we really like an 850, and eventually, we go to the 1,000 CFM and beyond. We know the tuning trends of those smaller carburetors. We're gonna find out if the same theories stick when you go big for large race stuff. So let me tell you all about the new configuration of the engine, then I'll come back and give you details about these carburetors. First, let me go through all of the stuff that is the same about this engine since the last time you saw it. It still has Almoroso oiling. The K1 Technologies crankshaft is still there. It's a 4.375 stroke, and with that 4.600 bore, it makes 582 cubic inches. The comp cam's cam is the same. It's a giant solid roller. The duration at 50 thousandths tappet lift is 284 on the intake, 300 on the exhaust. It's about 850 lift on both valves. The lobe separation angle is 114. To make that survive, it's on a 55 millimeter bearing. And of course, the heart of it is the same, which is the Dart tall deck aluminum block, which is like one of my most prized possessions. I love the aluminum block. It's such a weight-saving goodness. Here's one of the key things. The old compression ratio was 14.7 to 1. I decided I wanted to convert this engine so that it could putt around on pump gas. I'm not talking about making wide open throttle drag race passes on 91 octane. I am talking about retarding the timing a few degrees, putting 91 octane in it, and being able to cruise it on the street. Yes, it can do that at 12.5 to 1 with this kind of camshaft and being all aluminum and being light on the throttle. So that's a major difference in potential power, going from 14.7 to 1 and dropping it to 12.5 to 1. So that's a big change. The top end is also way different. It now has Brodix BRX cylinder heads on it. These are an as-cast, meaning unported version of the very popular Brodix SR20. The intake ports on these things are 444 cc. They can flow up to 495 CFM advertised. It's a big 2,400 intake valve, and for that reason, the intakes are manly titanium. The exhaust, are gonna be in canal. And of course, I got giant manly springs on the thing now. The intake manifold is now also a Brodix. You've seen us run this with an Edelbrock 4-barrel and also with a tunnel ram. Now it's a Brodix that matches the heads, and it's extensively ported by Bostik racing engines. Speaking of Bostik, man, I really got to throw James Bostik in Yuma, Arizona, a giant thank you, because he jammed this thing together with a lot of parts availability problems in no time to make it happen for this episode. And then, of course, there's the carburetors that I will tell you all about. But first, I got to admit, I'm dying to know how much power this thing makes now. It used to make 1,000. I'm really hoping that it'll still do that, but I did reduce the compression ratio quite a bit. So I'll find out at the same time that you find out. Now let's discuss what we're gonna do with the carburetors here. We did this once before on an engine that only made about 470 horsepower, and we tested like a 650, 750, 850 or something like that. And I'll just give you the basics of that because I know it's useful to a lot of people. If you're working up to about 350 horsepower, a 600 CFM carburetor is fine. Up to like 400, 450, you're good with a 750. When you start to tickle 500 and above, we really like an 850, and Dulcich and I will use a 950 every single time when you're talking about something that's like 575 into maybe, you know, 675, and after that, sky's the limit. You start to go to these, which are 4500 series carburetors instead of the smaller 4150 series. These are the ones that take the much bigger footprint. They're commonly called a Dominator because that's the Holley brand for them. Now, when we were doing the smaller carburetors, we saw some tuning trends as the carburetor got larger and larger, and I think we might see the same thing here. What I don't know is if there's such a thing as too large a carburetor for this engine. Let's talk about how the manufacturers get more CFM through a carburetor. It's fairly simple. It's the throttle valve size. Just the barrel gets bigger and bigger. For example, the 1050 carburetor has a 2-inch throttle valve size, or butterfly. The 1250 is 2 1/8, and the big 1450 is 2 1/4. Now, why might that affect you adversely? Because we know that on the dyno, you can put almost the biggest carburetor that you can get, and it'll ultimately make the best horsepower because at that point, the engine's only gonna use as much air as it can. So what's the downside? To explain that, let's look at how a carburetor venturi works. First, there is a booster in the middle of the venturi. This is what brings the gasoline. It's got holes on the underside of it that the gasoline is drawn through. The venturi is sort of an hourglass shape. Actually, in these, it's not at all. It's a taper, and then they're straight, and then the booster provides that venturi effect. The venturi effect is basically Bernoulli's principle, which is that as airflow goes across a restriction, the air speeds up. We also know that fast-flowing air is a lower pressure area than slower moving air. So what the venturi is doing is creating a high pressure area above that booster and a low pressure area below the booster, and so it's drawing that fuel out. It's basically sucking gas out of the booster. Now the thing is, as the hole gets bigger and bigger, the airspeed slows down. And what you're really matching is the airspeed versus the engine's displacement, RPM capability, and horsepower, because you want the air to be able to pull the gas you need. If the engine's incapable of drawing the air through fast enough that it pulls that gas out in an efficient way, you've got trouble. So that's what we're gonna be looking at. And here's a clue as to how the manufacturers know that larger carburetors need larger jet sizes because they don't suck on the jet hard enough to flow enough fuel. The QFT 1050 comes from the factory with a 92 jet. The 1250 comes with a 94. The 1450 comes with a 96. So they have a bigger jet size with the larger barrels. A lot of people think a larger CFM carburetor flows more fuel. Don't put that carburetor on there. That's way too much gas for your engine because it's too big. It's an 850. Wrong. The jet size really has to go hand in hand with the venturi size and the signal that the jet gets. Here's another thing that we're going to be looking at tuning on these carburetors. When you buy a Dominator and sometimes a race series 4150, you can pick from what's called a 2-circuit or a 3-circuit. Now, these circuits deliver additional fuel, and you've got an idle circuit, you've got a high-speed circuit, and on a 3-circuit carburetor, they add an intermediate circuit. Steve Brule always likes to run a 3-circuit carburetor on an engine like this so it can deliver enough fuel. Let me show you the discharge for that intermediate circuit. If you look down the barrel of the carburetor, maybe from the underside, you can actually see that little tube sticking out. That is just delivering more fuel as you go. Thing is, all of those circuits deliver what's called an emulsion. It's a mixture of gasoline and air, and they have air bleeds at the top of the well. Here's why. Imagine when you're drinking a soda and you've accidentally broken your straw in half and it's got a little hole in it, and you suck through it. You get a bunch of air. It's not that satisfying. If there's no hole in it, you get straight soda. If there's a giant hole in it, you basically can't suck through it enough to get some soda. The same thing is happening with those air bleeds. You take that jet out of there, you're hardly going to move any fuel. And that's a trick that Brule uses to sort of disable that intermediate circuit if he doesn't need that much fuel. You're also going to see us messing around, probably not with the idle air bleeds, but with the high-speed bleeds to make some tuning differences with these carburetors. So that's about what you need to know as far as technology in these things. Otherwise, they're just organized leaks. What we're gonna do is run my engine first with a 1050 CFM carburetor, and that's when I'm gonna find out if this thing still makes 1,000 horsepower. Probably not with the 1050. It probably makes more power with the 1250. I honestly have no idea what happens with the 1450, and that's why we're here. Let's go talk to the Steves, including Steve Brule, the carburetor whisperer, and we'll get this thing going. Okay, guys, I'm happy to have my 582 back. Do you remember how badly we splattered the dyno cell with this thing before?
No, it was brutal.
Oh,
what
man.
a heartbreak, Freiberger.
It really was devastating. So our very first test here is not only going to be the 1050 CFM carburetor, but also the first time I'm gonna be witnessing the new power with my old new engine. This is one of those things where guys go, what do you mean? This thing used to make X amount of power. And you go, well, yeah, but you changed the compression ratio, the cylinder head, the intake manifold, the headers. Yeah, so we'll find out what kind of power.
I will simply say you clipped its wings in your attempt to go street driving.
Clipped its wings. That's not a kind way of putting it. Yeah.
All right, let's find out. I want to know.
All right, let's go.
This thing used to make 1,008 to 1,015 horsepower naturally aspirated with a 4-barrel, and it's now making 953.6 horsepower at 7,100 RPM and 753.8 pound-feet of torque at 6,200. So it's down like 60 horsepower, and that's probably 2 points of compression.
That's not a surprise. In fact, if you look at some prior episodes where we were talking about 4% in that sweet spot of 10 to 12 and maybe 3 on the other side of that, you know, 6%, that puts us kind of close right back to where we were. So I don't see it as a surprise at all. I think it's doing exactly kind of what you wanted it to do.
Let's talk about what you did in the tune-up, because I think that's going to be a big part of what we're going to see between these 3 carburetors, because I've got the specs right here of what they come with from the factory. And so it came from the factory with jets of 92 in the front and 92 in the rear. What did you do to tune this one up? Because I'll compare that later to the other carburetors.
Initially, my suspicions were I was going to put it on and it was going to be rich. And I put it on and it was lean with the factory jets in it. So I just took out the baseball bat and took the big swing. I went from a 38 air bleed, I believe is what it comes with.
High speed, yes.
And I went to a 23.
Oh, really?
Because what I find is when you start trying to rejet in that 93, 95, 97 range, it doesn't do anything.
Yeah.
So I put a very small high-speed air bleed in it to move the jetting way down. And actually, I needed to add about a ratio and a half of air fuel. Got it back down into the low 12s, high 11s, and then...
High 11 air fuel ratio.
Air fuel ratio. And then I jetted it down by, I believe it was 4 sizes in the front and 3 in the rear.
So you went from 92, 92 to 88 and...
Yeah, 88 and 89, I believe it was.
Okay.
So this power curve, I've been on the rich and lean side of it, and this seems just fine. I've been on the high and low side of the timing, and this is the power it makes.
So we will attempt to match at least this peak power air-fuel ratio with the other carburetors.
Yeah, and no two carburetors are absolutely identical. We'll see a little change here. Maybe the way it comes in is a little richer, a little leaner, but overall it's going to be very close.
All right. Let's step it up. We're going to go install the 1250 CFM carburetor.
Bigger.
Yeah. We're doing a carburetor size test and we're making power. My 582 big block Chevy just picked up 30.7 horsepower and 16 pound-feet of torque simply from going from a 1050 CFM carburetor to a 1250. So that makes me super happy. It's just a matter of airflow, same as when you change a cylinder head. So that was really cool. The big deal that I wanted to look at, though, is the tuning between the 1050 and the 1250. On both of them, Steve had trouble getting enough fuel in the engine, which is actually, to your point, why you run the 3-circuit carburetor. Listen just to the specs of what he did on the 1050 versus the 1250. Starting off with the air bleeds, the little jets that are in the top of the carburetor, he had a number 32 primary and a 23 secondary in the 1050 carburetor, whereas the 1250 took 23 in both positions. So the smaller number means less air, which means richer, more fuel. But then the jets are really an eye-opener. On the 1050, he was running an 88 and an 89 jet, and then on the 1250, it's got 102s in it. Let's actually look at the power overlay between the 1050 and the 1250, just in case we haven't already made our point. And by the way, all the discussion of tuning is to bring you to the conclusion that Steve got it set up at the same air-fuel ratio. The curve's not precisely the same.
Close as I could.
But at peak power, it's very, very similar. And by the way, we ran them both with the air hat up top, which does affect power because of the way it directs air, but we'll get to that in a minute. There's your power curve overlay between the large and small carburetor. Clearly the black lines there are the 1250, the red lines are the 1050. That
is absolutely mind-boggling to me. I mean, that's just a huge change for a 200 CFM difference in a carburetor size. I would have bought 10, I would have even bought 12. 30?
30.
Oh, hell.
And it picked up a lot of torque, too.
Yeah.
Wow. Now, let's go look at why, because I bet you if you look at the airflow overlay, and this is CFM readouts from that air hat, we're going to see a significant change as well.
And there you are. It's a difference in airflow.
Okay, there you are. That's a difference in airflow. Black line's obviously the bigger carburetor. The real question here is you saw that the power curve was way different, even all the way down here, but the airflow is the same.
Yeah.
Could it be quality of the fuel
What else can it be?
Sent out of the booster?
Well, droplet size.
Droplet size? Maybe there was so much pull on the 1050 that it was doing something weird. You would think that that would like make a smaller droplet size, but maybe not. All right, the next thing we're gonna do is bolt the 1450 carburetor on here. And like, here's what I'm gonna need you to do. I need you to just go ahead and make the 1450 deliver another, what was it? 16 horsepower so that I can have my 1,000 back.
That's what you need me to do.
That's what I need you to do.
Yes.
Okay, well, your wish is my command as usual.
Basically, our 1050 CFM carburetor made 953 horsepower. We put on a 1250 and saw 984. We put on the 1450 carburetor and we saw 986.9 horsepower and 765.5 pound-feet of torque. Well, how about an overlay? Compare that 1450 to the 1250. Yeah, not much of a change there at all. No. As a matter of fact, the 1450 made less power right through the middle than the smaller carburetor, than the 1250, which tells me, I think, that's just what the engine consumes, right? It's got a restriction someplace else.
Yeah, and Really? I mean, can we look at these airflow numbers and see if it did, in fact, flow more or less air?
The black lines here are the 1450 carburetor, and the red ones are the 1250. It did move a little bit more air up top.
A little bit.
But it didn't use it to make horsepower.
Quantity is not always quality.
No, I think the fuel dribbles on a booster when the Venturi is way too big and the airspeed's too low.
Higher airspeed through the carburetor may actually end up being higher airspeed through the intake manifold. Again, quality of air and how it fills the cylinder, not just how much. And
let's talk about the tune-up on the 1450. It was the easiest one.
So easy.
Why? What happened?
I think the factory calibration is obviously different in other circuitry in the carburetor, but look, what I can tell you is with all of the factory air bleeds in it, the factory jetting, everything, I bolted it on, and the thing was like a touch rich. And so I took 3 jets out of the front, and I went a little left, a little right of that to be sure I wasn't leaving anything on the table. And what it ended up being is it took the 96 jet it comes with in the secondary, and I put a 93 in the primary, and that was that.
It's interesting then, because what it means is the 1450 was easier to tune just for whatever reason on this combination and this calibration, but made the same power as the 1250, which was kind of a hassle to tune and ended up with a giant jet in it.
Wow.
But the 1450, I wouldn't say, oh, I'm gonna buy that carburetor because the tune-up was easier. I would still buy the 1250 and just do a little bit more fiddling.
The reality of it is any one of these 3 carburetors, in my opinion, is gonna take an air-fuel ratio meter if you're in your car, or have it at the dyno and have somebody that knows what to do with it. Because if you're gonna even attempt to drive something like this on the street, it's gonna take a significant amount of changes in the primary circuitry, certainly.
Which really ties into the first of my conclusions. No matter what carburetor you buy, you're gonna have to fiddle with it, as you were just saying.
Yeah.
At this level, there's just no such thing as the out-of-the-box tune, plop it on, drive it down the road, and it's happy. I think the last thing, although we didn't really see it here, maybe it has to do with why we didn't have power with the 1450, is that there is such a thing as quality of air and quality of fuel distribution that is beyond what we can measure or see.
Yes, agreed.
My final conclusion on this particular engine is that, knowing what I know now, I want to go get a 1250 or maybe even a 1350. I know you'll pressure me into that.
Oh, yeah.
It actually has power valves, and bring it out here and have you do the brûlée treatment.
You know, this is still, out of all the motors that we've done here, this is still my favorite.
It didn't make 1,000 horsepower this time.
It's still my favorite. It has those bars on it that kind of fix any of those problems.
We can solve these problems with that individual port nitrous system that's sitting on that thing. That sounds to me like a future episode of Engine Masters. Throttle body, self-learning, super simple fuel injection. It's the hottest thing in the aftermarket, and the latest is the Holley Sniper 2. But how do you install it, and does it even work? And is it better or worse than a carburetor? You're gonna see all of that this time on Engine Masters. You know, I've talked to a bunch of hot rod building shops, and they tell me that one of the #1 things that they get these days is people coming in the door and saying, I don't want my carburetor anymore. I want super simple, super cheap fuel injection that isn't gonna kill me with a laptop and things like that, which is why these throttle body EFI kits are so popular. There's so many different companies making them these days. In this episode, we're gonna try the latest one, the Holley Sniper 2. Now, I got to admit, over the years, we haven't been that impressed with these things, but this promises to be a little bit different. I mean, you know that a carburetor's an organized leak that relies on airspeed through some venturis to draw fuel to run properly, and it has a bunch of mechanical systems in it to handle the idle circuit and things like that. Real, quote, EFI is port EFI, where you get an injector in each runner of the intake manifold, and you've got fuel that's dedicated just to each of the individual cylinders in the engine. And we know that's highly tunable. We know that that's what people use in race applications all of the time. Then you've got the middle ground unit right here, which is throttle body EFI. Almost all of the aftermarket throttle body setups have like an annular ring in there that sprays gas down the barrel, and it's got no booster in it like a carburetor would, so they also tend to flow more air. The thing about them is that they're electronically controlled, and so they can deliver the fuel more precisely than a carburetor. But the problems that we've seen with them in the past is that they maybe don't have as good a cylinder-to-cylinder distribution. We've seen dead holes with these things, depending on the intake manifold that you run them on. And also the so-called self-learning feature of them is either a hit or a miss. So the Sniper 2 promises to solve all of those problems, and that's what we're gonna find out in this episode. So we're gonna look at the Sniper 1 versus the Sniper 2. These are both from Holley. They've sold the Sniper 1 for years. Dulcich and I have even installed them. There's nothing really wrong with them, but they're making them much better. They say that there are 14 features that are brand new about the Sniper 2. Let me talk to you about the ones that affect my life. First of all, this looks way cooler. If you look at the Sniper 1, look how it's all fat this way. It looks like a thermoquad carburetor, and that's actually a benefit to Dulcich, but I don't dig it as much as the narrower look and profile that is here on the Sniper 2. Also, look at the entry into the barrels on the Sniper 1. You can see it's got sharp edges here, where there's more of a radiused entry on the Sniper 2 that promises to have more flow. You can see that the computer is up front on the Sniper 1. It's on the side on the Sniper 2, but more importantly, they say that there's more electrical noise resistance in the new one than there was in the old one. That's a big deal with EFI. Electrical noise can just trash stuff, and that's gonna happen less with the Sniper 2. Now focusing on the Sniper 2, this thing is advertised to work up to 650 horsepower naturally aspirated. It has 400 pound per hour injectors in it, and it'll work at 570 horsepower boosted. The reason it's a lower number boosted is that when you put pressure on these holes that are discharging gasoline, you're working against them, so it can flow less fuel, so it can make less power. The other thing is, while they can both control your electric fans based on the temperature of your engine, there's more outputs on the Sniper 2. You can set them up so that you can do nitrous systems or anything like that. There's 2 grounded outputs, and then there's 1 that will work in proportion to your throttle position sensor, so that's pretty cool. And while both of these are self-learning, you can also plug in a laptop and get more refinement out of either one of these, because both of these are simple enough that when you make an air-fuel ratio change with the handheld, it does it globally, not just in one area of the map. So now that I've brought that up, let me tell you about how the self-learning thing works. The self-learning deal really started as a marketing pitch for people who absolutely did not want to have a custom tuner on a laptop in order to have EFI on their engine. They just didn't want to take those steps. And honestly, it's becoming closer and closer to true these days. Here's how it works. When you go on the handheld device, before you first fire the thing up with your throttle body EFI, you tell the system a lot of your engine parameters, like the camshaft you're using and the displacement and things like that. I'll get into it once we actually make it run. But once you've told them what your engine is, then it picks one of many fuel maps that they have pre-made at Holley and loaded into the computer. It picks one. Then you can drive the car, and what it does is it compares the actual air-fuel ratio as measured by the O2 sensor in the exhaust to what has been commanded by the base table, and the readout will show you whether it's having to add or subtract a percentage of fuel to hit the mark. Then there's a second table that's called a learning table, and that one sort of memorizes what needs to happen to hit the air-fuel ratio that you've commanded, and that table is what ultimately the system reads, is that learning table, so that it's modified the base table and it says, here's what we thought you need. The learning table is what it actually needs in real life, and that's what it runs off. Your goal is to get the thing to run off that learning table so that the computer isn't making huge corrections like adding 20% fuel. It's down to adding just like 2 to 5% fuel to get the thing to run right, and that's how you get it to be super smooth. Now, we're gonna test it versus a carburetor, and I'm gonna show you exactly how the installation works on these things. Then we're gonna show you how to make it self-learn, and then we're gonna pull the handle on the dyno and see if there's actually more power or greater drivability or a better fuel curve with the throttle body EFI than there is with the carburetor. The engine we're using here is from Jeff Ginter Racing Engines. We appreciate the loan. This is basically a spec motor that they use in a certain class of off-road racing. It's extremely similar to a GM CT525 crate engine, but it actually starts as the regular 376/525 crate engine. If you don't understand that, let me keep it simple. It's a 6.2-liter LS3-based engine. Ginter has gone in and added forged pistons and done some oiling mods for reliability, but it's basically the same as a GM crate engine. And in the CT version of that crate engine, it has to use a carbureted intake manifold, which is what we're doing here. This is an Edelbrock Victor Jr. And up top right now, we've got a Brawler 750 double pumper on it. The ignition is going to be controlled the whole time by that MSD LS box that can read the wheel on the crankshaft in these things, send the spark at the right time. It plugs into stock coil packs. And so we're not controlling the ignition with the EFI in this case. We're gonna run first with the carburetor, and second, we're gonna start that tune-up process and decide if the Sniper 2 is super awesome. We just found our baseline power. 508.7 horsepower at 6,600 RPM. The torque, 459.7 at 5,300. Now we're removing our 750 CFM Brawler carburetor, and we're gonna switch over to the Sniper 2. One thing you do have to pay attention to is you're gonna need about 60 PSI worth of fuel system. So we're changing from our Aeromotive carbureted regulator to our EFI regulator. Now we get into the wiring part of the program. Holley advertises this as only having a 4-wire hookup, like battery plus and minus and switched ignition. That I go into tuning, basic fuel, and then target AFR, and it comes loaded with the AFR at idle is 13.5 to 1. I think that's good for this. The more radical your engine, the richer that may need to be. Target AFR at cruise, they've got that at 14 to 1. I think I'm gonna take that down to 13.5 as well. And target AFR at wide open throttle is already pretty good. So we're just gonna leave that there. We're gonna cruise it, and I'll show you what it does when it's self-learning. And then, of course, we'll start to make our power pulls. Steve fired it up a minute ago, and it ran perfectly right out of the box, at least at idle. Now we've got a little bit more to do. Let me just tell you what we're gonna be looking at. Closed loop status and learning status. Closed loop is when it gets above 160 degrees of coolant temperature. That's when the O2 sensor starts to interact with the computer and modify the air-fuel ratio to give you what you need. That's the point at which the base map, it starts to interact with the learning map so that the learning map can learn. That's when learning turns on. What you'll see once it's learning is two things: the closed loop compensation percentage, and over here, the current learning percentage. What that is closed loop compensation is how much fuel does the system have to add or subtract to modify the base map. Let's just say the base map, to simplify things, is saying, please deliver 10 units of fuel, and it really wants 11 units of fuel. Then you will see a 10% compensation plus. It'll say plus 10% compensation because it's adding one more unit of fuel. And then the learning percentage is, it'll start to say, okay, that's what the engine wants at this RPM and load. And it'll tell the learning table, modify the base map by this much to hit this target. And the goal is so that it's not having to make as big of a change all the time. The goal is to get it running seamlessly, as close to 0% learning as it can. Now Steve's got the engine running, and what we're looking for is for the open loop and no learn items to turn green. There you go. Now we've got closed loop right there, and next you're gonna see the learning light change to green, which will tell us that it's gonna start to feed information to that learning map I told you about. We need the coolant temperature to get up above 160 degrees. See how the closed loop compensation is 4%? It's adding 4% fuel. Oh, now it's all the way down to 0 and 1%. And you can see that the learning is at 0%, so it's already figured out what to do right there. The learning map has already been corrected over the base map. You saw me go in there and set everything on the handheld device, but after that, we wanted to have the computer learn a little bit so that we trusted it to go wide open throttle for a pull. What was your tactic on teaching it?
Basically, I just took it at 3 different RPM points initially. I went 3,000, steady stated it for maybe 4 or 5 seconds, and it learned really quickly. Then I went to 4,000 and 5,000, not really expecting it to interpolate between those, but just giving it some points so when I did do a transient test, it wouldn't be wrong for very long if it had to learn in between.
Normally, that's a process you would do in the car, not bringing it to 3,000 RPM wide open and holding it, but just driving it at a bunch of different throttle positions. And if you see a spot that's really lean, I mean, don't hurt your engine by giving it a whole lot of load of 14 or 15 to 1. But if you can drive right there, we did this on the Impala, and watch it rich enough and meet the target. It's tuned up, but is it at the point where you trust it to go for a full pull?
I trust it.
Then you know what to do. We actually made 2 pulls, and here's our base power numbers with the Sniper EFI: 520.8 horsepower at 6,600, 467.4 pound-feet at 5,300. So that might sound to you that it's better than the Carburetor, and it is. Watch this. Black lines here are the Sniper, the red lines are the Carburetor.
It really looks sloppy there in the bottom of the curve up to peak torque.
I thought you all you cared about was high RPM, where it made tons more power.
I don't want to give up all that torque. The Carburetor obviously was better.
Yeah, look at this gap right here. Steve nailed it. This is the EFI, the black line. It's way worse than the Carburetor. And so we said to ourselves, why would that happen? And so we went and looked at the 2 air-fuel ratio curves for these 2 pulls. Red line's Carburetor, black line's EFI. The Carburetor is going way rich and then making a big whoop-de-doo and then going down. But then the EFI starts really lean up here and then comes down, and to be honest, is fairly flat. This might look a little bit jagged, but you're dealing with 0.25 of a ratio. This is from 12.5 to 1 to 12.75 to 1. So that's actually pretty good. So we said to ourselves,
why is it so lean down there? I mean, that could be the difference in power.
That could be the difference in power. Let's look at first the air-fuel overlay after we tuned it up. And there's the results of our tune-up. Not only is it globally richer by half a point, but it's not making as dramatic of a swing here.
But this is where it was down on power, and richening it up brought the power back. When we first looked at it and thought the carburetor was rich, the carburetor was really right for that RPM range. It made more power.
We didn't train it as much as I thought we did, but we did make it all richer, which was so easy. It was like, done. And watch what that did to the power curve.
Boom.
Whoa.
Now, all of a sudden, after the tune-up, look how much we improved the Sniper power down here. Incredible and super easy. Usually, we don't see that kind of power swing on 1 point of air-fuel ratio.
Not every cylinder is going to be exactly what that collector was reading.
There you go.
So I think we saw maybe more improvement. It's so close, and what's interesting to me is we can almost follow the power with the air-fuel ratio stuff down here. I'll bet if we go back and look, there's a little dip there. The more this thing is driven and the smoother it gets, I think the better that gets overall.
So we know that our tune-up made a huge difference. It was super easy. I don't think you can do that with a carburetor. You can't pick an area, wide open throttle, or pick an RPM at which it's gonna make richer or leaner. It just doesn't work that way.
No, it doesn't. I mean, you know, when you look at carburetors, race carburetors, whatever the application, you can kind of pick a sweet area. You can get it to be really pretty flat within 1,500 or so, but when you get it right at 9,000 RPM, it's not right at 4,000 RPM, and that's just the characteristics of the airflow and how it signals the booster. EFI, on the other hand,
super easy. Although, on the Sniper 2, on the handheld, the only choice you have is to change air fuel globally.
Yeah.
You can plug into it and tune it with a computer, which, by the way, Ish here at Westech does on the chassis dyno like every day. Yeah, so you can go in and tune it up, but nonetheless, that simple change
That's very good
awesome.
For a self-learning program with you're just setting a global air-fuel ratio. Give me 12-to-1, and then boom.
Boom. 12-to-1.
This is end user in your driveway on a Saturday, honestly,
Right.
kind of installation when it comes to this thing. And through that handheld, basic parameters, I mean, it gave us a map that was that fast to start, and it learned really fast. I was amazed.
But then, why does the EFI make more power than the carburetor? Simple answer, CFM.
Bigger.
Airflow, and that is backed up by the fact that the power is the same up to the point where you pick up engine speed and have more airflow demand, and then it starts to separate.
The lesson for me here was just that this thing's cool.
Way better than we had seen before in this application. I'm going to reserve that because we had more problems on dual plane intake manifolds than single planes.
Yeah, but so far to me, it's very convincing because this generation, it's pretty much plug and play. In the last two experiences I've had, I haven't seen it all, but like your car with the supercharger and now this, I think I want one, David.
Whoa!
Yeah.
Whoa!
I'm really embarrassed to almost say this, but I think I'm with Dulcich. I would head this direction myself now, and you know me, I'm the last carburetor guy standing. I mean, it was amazing.
So conclusion number one is that we're all super impressed and borderline converts to this deal, which surprises us. Number two is that, you know, the tunability of this thing is fantastic.
Yeah.
Number three is we made more power with the EFI than the carburetor. I don't think that's fully a thing. You know, I'm not saying EFI makes more power than a carburetor. I'm seeing a larger throttle body makes more power than a smaller carburetor. Maybe in the real world, you're stuck with that smaller carburetor for drivability.
That's just what I was gonna say. In the real world, that's the carburetor that a guy would probably have on it. So
maybe it does make more power.
This does make maybe a little more power.
Yeah.
There are carburetors certainly that will match this as far as wide open horsepower, but is that the same carburetor you have on your street car?
Right. And then the last thing is we're not really able to determine drivability with this thing on the dyno. We've experienced it on a supercharged application on top of a roots blower where it was really good. This seems to drive okay on the dyno, but we don't know about snap acceleration, you know, we don't know about steady cruise.
I'm gonna disagree with you just a little bit.
Yeah?
Because I can drive those things on the dyno a bunch. I've had companies come and say, can you drive it on the dyno because we can't on ours? I think it's gonna drive well.
It's not the in-car real world, but I'll take your experience and I'll also say this. If you do have a problem with it, you can tune some of that stuff like accelerator enrichment on the handheld, and you can always plug it into a computer and make it great.
Yep, I agree.
Right? Wow. EFI converts. Who knows? Maybe you'll never see another carburetor on Engine Masters. Yeah, you will. Nitrous oxide is the greatest. It makes power so easily, but do you want the plate system or the direct port system? We're gonna answer that question and show you stuff you probably didn't think about this time on Engine Masters. Man, Man, I love nitrous oxide. It's so simple. All you do is take this liquid out of a bottle and you inject it into the engine. It turns into a gas. You add some fuel to it. It like chills the inlet system hardcore. When it gets into the cylinder, all of that compression and heat makes the nitrous break up into oxygen molecules that let you burn more gasoline, that let you make more horsepower. And you know what? I've done it all of my life with what they call a plate system that goes underneath the carburetor and just simply shoots the nitrous and fuel down in there. I've only ever done like maybe a 250 to 300 shot personally, which is why I've gotten away with plate systems. However, there are people who run up to 400 or 500 horsepower with a plate. That's hardcore. What's really hardcore is direct port nitrous oxide. What this does is sprays the nitrous and additional fuel right there in the port. Think of it like the difference between throttle body fuel injection, where the gasoline sprays up here, the same way a plate sprays a nitrous and fuel up here, versus direct port EFI, where the injector is down by the cylinder. That's the difference that we're looking at here, and Steve Brule has told me that even at the 300 horsepower level, there's big benefits to running direct port. And that's what we're gonna be investigating in this episode. What I'm gonna do first is tell you about the engine we're gonna be using for testing, and then I'll get into details about the nitrous system that we're gonna be using. You may recognize this engine because it's been on several episodes of Engine Masters. It's the one that I first put together to make 1,000 horsepower naturally aspirated. But there's some stuff that's different about it from before, so let's talk about that. It's a 582 cubic inch big block Chevy. It uses a Dart aluminum tall deck block. It used to be 14.7 to 1 compression. I have dropped that to 12.5 to 1 so that I can put it around on pump gas. And honestly, that's gonna make me feel safer with the nitrous too. I think nitrous is a little riskier with higher compression, even though it makes more power. It's got the same camshaft it used to. It's a big solid roller, 284 and 300 duration at 50, 850 lift, 114 lobe separation angle. The big change now is that it has Brodix BRX heads on it. These are an as-cast head. They are not ported, but they're extremely similar to the Brodix SR20, which is the hot cylinder head these days. It's a 20-degree deal, massive intake port, 444 cc's. They flow 495 CFM advertised, and so that's a trick unit. We're gonna see how those work. The intake manifold now is also a Brodix, heavily ported by James Bostic at Bostic Racing Engines. And the other thing that he did is a spectacular job bending up all of the lines and installing our direct port nitrous system. He spot-faced the pads on the intake manifold. Like, Brodix gives you a little cast-in pad to put a nitrous nozzle, and he machined them down nice and flat, tapped them in, put this in, and did just a killer job bending all these lines. The look of direct port nitrous just says serious action to me. I love it. Now, up top, the carburetor is gonna be a QFT 4500 series, and it is 1250 CFM. So that's our engine. It makes 986 horsepower at like 71 or 7200 RPM. And of course, we're gonna bump that up way over 1,000 with nitrous oxide. Let's look at how we're gonna do that. All of our nitrous kits here are coming from Nitrous ProFlow. That's a division of Wilson intake manifolds. We love the quality of their stuff, and I'll say I've never used a nitrous plate like this. The nitrous plates have spray bars in them that carry the nitrous oxide and the enrichment fuel, and usually they're a tube that's pressed into an aluminum plate, and these are billet and cut in one piece with the plate. It's actually really trick, and they use what they call fan spray technology. Usually there's just holes in a plate and they squirt out nitrous this way and fuel this way. These apparently squirt it all out like this so that it's more of a fog across the intake manifold to try and improve cylinder-to-cylinder distribution. And we're only gonna be spraying about 300 horsepower worth of nitrous oxide. So the question is, if you can do that super easily with the plate, why would you ever go to the direct port system? Well, the direct port is usually really hardcore for guys who are trying to put in like 600 or 700 horsepower, or even if they're using a plate and a direct port system together. But Brule told me once again that there's real advantages to this. The big advantage to me is that it looks so cool. I think the originator of this, or at least the popular thing, is an NOS brand fogger. The fogger's a direct port kit. A lot of people refer to these generically as a fogger, but this is a Wilson, so that's not the brand name, but it still has that look. They use what they call a V-force nozzle. This nozzle goes into the intake runner, and it's got one hole in it for gas and another one for nitrous, and it sprays it right there at the back of the valve. And the thing is, when you do that, you end up having jets in each individual cylinder. The plate system has a fuel jet here and a nitrous jet here. The jets have different orifice sizes, and that's what determines how much nitrous you put in the engine, how much fuel you put in, and the nitrous and fuel mix determines how much horsepower you're gonna make and how rich or lean the system is. So while you've only got 2 jets in the plate, you've got 16 in the direct port setup. With those 16 jets, 2 per cylinder, you get a lot more discretionary tuning over each individual hole in the engine. But does that even matter at 300 horsepower? That's what we're here to find out. So we're gonna run this thing with no nitrous at all so you see what kind of grunt that it makes. Then we're gonna go to the plate system and get that refined. And finally, we'll go to the direct port system, try and make it match the same horsepower level that we did with the plate, and start tuning individual cylinders. This is gonna rip. We're gonna make way north of 1,000 horsepower. We're testing various nitrous systems on my 582 cubic inch big block Chevy, but first we needed to know the power off nitrous, and it's actually pretty stout. This thing makes 987 horsepower at 7,100 RPM and 780 pound-feet of torque at 6,200.
For 12.5 to 1, it's good.
Next step is going to be nitrous plate system and seeing how that works out. Yeah. What's our tune-up going to be on that? What are you gonna do with timing? What are you gonna do with jet? How much power are we gonna make?
You've asked me way too many questions all at once.
Okay.
I can tell you that my intent is probably, once again, to be a bit conservative. I'm gonna pull out ballpark numbers, 4 degrees per 100 horsepower increase, plus a couple extra. I'm gonna be conservative. We're gonna start with Wilson's recommendation for a 275 shot. I've got to go look at what those jet numbers are, but in the past, we've seen that the Wilson stuff kind of typically makes a little more power than what it's advertised to be. So if we're really shooting for 300, I'm going to actually target a 275 number because I think it will go over.
And naturally aspirated, we're running 37 degrees of timing.
Yeah, so we're going to knock it back, basically 12 or 13 degrees out.
Yeah, put 22 degrees in it.
Yeah.
And we've got it on the MSD so that when you hit the button is when it pulls the timing, right? We better verify that.
Yeah, it's actually, we always do. We go through that step, and the first thing we look at is check the solenoids, then we verify the timing with no fuel or nitrous hooked up. Then we hook the fuel up, purge that solenoid, then finally the nitrous. The other thing that we're actually able to do, this is a digital 7, you can do it with the grid as well, is when I activate the nitrous solenoid, it instantly pulls the timing out. But when I release the button from testing, it actually keeps the timing out for an extra half a second.
That doesn't bother me.
To make sure that all the residual nitrous in the cylinders is now gone out, to make sure that there's no potential for detonation at all.
That's pretty trick.
Yeah.
All right, so let's go take those precautions, tuning this thing up, and then we're gonna run the plate nitrous system and start to look at some of the cylinder-to-cylinder distribution on that thing. And of course, the power. We've gone through all our safety checks. We did some initial runs tuning it up with a 225 horsepower gain. Now we have it jetted for 275, and we think it's gonna be good. It might even make almost 300 horsepower with this kit. Let's find out. We've just gone as far as we're going to go with the plate, and we've got it jetted for what Wilson says is a 275 shot in their kit. and it actually made 290 horsepower. Here are the numbers: 1,277 horsepower at 6,600 RPM and 1,035 pound-feet of torque at 6,400. Those are gonna wiggle really depending on where you press the button, but for what we're doing here, we're gonna have a comparative analysis. There it is. You can guess where Steve hit the button.
In my brain, I'm thinking 5,700, but you know.
I will also say that the hit is softer than what we've seen sometimes with plate kits like this.
With Wilson's recommendations, we actually have about 3 more degrees out than I have seen some other systems recommend.
Like you retarded the ignition timing 3 extra degrees.
Yeah, so it actually has 15 degrees out with a 275 shot. And I think that helps that really abrupt hit, you know, where it's just a touch softer, which I think is a whole lot safer for the engine, to be perfectly honest.
Bam, straight up.
Yeah, because, you know, that's where it's going to detonate, is with all the timing in it, and when you first activate it, that's where the most pressure is. So I like having the Wilson type tune-up with a couple, 3 extra degrees retarded.
You're also hitting the button way later than many drag racers would. He's hitting the button basically 6,000 RPMs where it begins to spike. If you were on a 5,000 converter, you'd be way down here.
I'm not trying to see what happens for 3,000 RPM.
No, we want to see
numbers. So.
I mean, really what we're looking for, I think, is the distribution and which one's safer.
Yeah.
And it's not even going to be which one makes more power, because who knows where the jets are exactly going to fall.
Yeah.
On that note, let's look at the cylinder distribution. Now we're looking at the air-fuel ratio in each individual cylinder. And if you just want to go, let's say, to peak power, which on this is 6,600 RPM, we can look at a range of the leanest cylinder is 13.8 to 1 air-fuel ratio, and the richest one is 11.6 to 1. In general, when we run a spray bar nitrous plate, we typically see that the distribution's not the same in every hole.
For me, it'll limit how much nitrous I want to put through a plate, because as you're getting more and more power, and if you have that variation, it could get more and more dangerous with more nitrous.
Yeah, if you jetted this for 400, for example, does that distribution get better or worse?
Well,
it might get better because there's more nitrous being
that's
sucked out of the roulette
possible.
wheel.
I've seen in some of the limited classes where they have to use a plate, where guys really get after it. But my personal opinion is kind of 250. 300 is the end of the road for a plate. After that, I think direct port nitrous is just a better bet.
Well, that's what we're going to find out, because I think a lot of hardcore nitrous guys are sitting at home right now going, 400 through a plate's no problem, Steve. And it might not be, but what we're about to find out is whether it's a little bit safer to have that port injection. And my honest hope is that we still have a distribution problem and that we can fix it with individual cylinder jetting.
And we can.
All right, so let's check that out. We're just going to do a quick changeover from the plate to the individual port nitrous. We just had a 290 horsepower power gain with our plate nitrous oxide system that Nitrous ProFlow says was only supposed to make 275 with the nitrous plate. That's pretty normal that it has a little bit more gain than they advertise. The jets in it are 92 on the nitrous side and 82 on the fuel side. Now, when we go to the port nitrous injection, the jets are going to be way smaller because there's 8 of them. So what Steve's doing now is just checking all of the jets just to make sure, because we haven't messed with this in a while. We don't want to accidentally have like one cylinder with a 400 shot or whatever. What are the jet numbers that we've got?
28 nitrous, 22 fuel.
And in your experience, that's a 250 shot that makes 300?
I'm thinking it's, you know, kind of recommended to be a 250, 275 by different manufacturers, but a lot of times it's a 300. I mean, it gets awful close to it.
Steve's gonna finish up making sure all of the nitrous and fuel jets are exactly what they need to be so that we don't overspray this thing, and then we'll run it, and hopefully it makes right about that 300 horsepower gain, and we'll see how much better it is or isn't in cylinder distribution. You missed it by a little bit. You said it might make 300 with the jets that they advertise as 250. It actually made 273 horsepower with the jets advertised as 250. Here's the final power numbers at this level. We made 1,260 horsepower, which is pretty cool, and 1,013 pound-feet of torque. Let me show you how close this actually is to the plate, even though it looks down a little bit. Dulcich doesn't like it. He always wants more. But let's overlay the plate on here. We have the plate system in red and the port system in black. You can see the gains that we saw are really right here at the hit. It spiked a little bit more. That's very close.
As it revs up, there's almost no difference at the very, very top.
Yeah, I mean, the peak went from 1277 to 1260.
This isn't a surprise.
No, it's no surprise at all. It's actually pretty good. So now we're gonna get into looking at the tuning, and maybe as we nitpick the tuning, we can pick that up and gain it back a little bit.
We hope.
Let's look at the cylinder distribution. If you remember when we were looking at the plate system, we had a couple holes that were leaner than we wanted and one that was fairly rich. It appears to be more even with the port setup, but I'm still looking at a cylinder here that gets as lean as 14.6 to 14.5 at peak torque. And then our richest cylinder is 12.8, 12.9, 12.5.
You know, those numbers may appear lean by kind of some recommended air-fuel ratio numbers. But in our past experience, at these power levels, you can run these things almost at the same air-fuel ratio as you would normally aspirated. In fact, there's some issues that actually occur that I know that you've seen, where when they're too rich, it can damage parts as easy as too lean. So I'm actually pretty impressed with that tune-up.
In my opinion, Nitrous wants to burn gasoline, and I think it could make more power if we richen up some of those holes.
I agree 100%.
I'm on board. So we've got number 1, number 2.
You're looking at which holes we want to richen up a little bit? I would do 1, 2, 3, 6. 1, 2, 3, and 6.
Yeah, 1, 2, 3, and 6, just to tickle more fuel in there, and who knows, that might pick up our power because we'll have more gas to burn.
We just did a tune-up to add 2 jet sizes to 4 different cylinders to add more fuel to them to even out the air-fuel ratios. We're gonna find out if that only made the tune-up safer, or if it also made more power, or neither. We just made our biggest power yet and our best tune-up yet. Here's what we did after we went in and richened up just 4 cylinders. You can clearly see on this graph that's actually like a bunch of spaghetti. The red lines here are before our tune-up, and the black lines are after the tune-up. We wanted to richen 4 cylinders. You can see those 4 cylinders are here. They're leaner, and we moved them right down. They're richer.
Imagine that. Did what we wanted it to do.
It doesn't always happen.
No.
Yeah, it never happens when I ask Dulcich to do something.
It's as easy as pie. You just throw those jets in there and boom.
Done.
You get that.
Well, I'm glad it worked exactly as expected. The thing is, evening out those air-fuel ratios in each cylinder did not make more horsepower. It just kind of doesn't matter, which is weird to me. Sometimes we see it like on tunnel rams, sometimes we don't.
We're in that window where, you know, 2 or 3 or 4 tenths may not matter.
But it makes it safer, in my opinion.
Absolutely, and that's kind of is always my target, is to make sure that the motor's safe. Then you can start becoming aggressive with it.
Now, because we've got the tune-up so good, Steve went in there and tickled 2 more degrees of ignition timing advance into the thing, which typically makes power, and it did. Let's look at those curves. The red lines here are when we had 22 degrees of total ignition timing, and then the black lines are when we edged it up to 24 total. Now, those will sound very retarded to you from a naturally aspirated number, and it's still very safe, but look at the power it made just from the extra ignition timing.
How much 10 or 12 horsepower makes at this point? I don't know. That's a ton of power any way you look at it.
Yeah, it's also just change the jet and you can solve that problem. The final power numbers are 1,268.4 horsepower and 1,022.8 pound-feet of torque. I guess what I learned in this episode is that Even if you want to run really low power levels of nitrous, because let's be honest, 300 is just getting started for a lot of guys who are running a direct port system.
Absolutely.
We've shown that that tuning with the direct port is absolutely worth it and gives you a base from which to grow and have your tune-up be safe.
Every time I see something get hurt with nitrous, it's because somebody comes walking in going, let's throw the 42s at it. I've had it that way in the boat. Let's hit it. And something goes wrong. I think this is the place to start. Now we've got knowledge, and now there's a place to move from to get to that 500 or 600 horsepower.
Your big message in the episode is start low before you go high.
Yes.
Yeah. The other thing I think I learned here is that really 300 horsepower, I'm still kind of okay with a plate system. I'd prefer the direct port, but the price gap is fairly significant. So is the complexity.
It is, and at 300 up, I mean, you can't really, the guy that buys a direct port isn't the guy who's going to be running 200 anyway. He doesn't need it. So he's got a price advantage there. But now on the way up, and the other thing about direct port, going back, is that you can't run 200 really very effectively. It actually becomes dangerous because the gasoline jet becomes so small that it can become plugged easily. So then you can damage something. So in my mind, 275, 300 is kind of the bottom end of the direct port stuff.
Yeah, agree. You can go up from there. It's just a jet change away, really.
And we survived the episode with my 582 in one piece.
Your 582, my favorite motor.
Yeah, that's great.
I like it too.
Yep. Whew. We'll try not to blow stuff up because we hate to do that every time we sit down to do Engine Masters.
Hello, xin chào các bạn nha. Các bạn ơi, hãy like của mình YouTube kênh của mình thật hay nhé. Cảm ơn các bạn đã theo dõi kênh của mình. Thank you các bạn rất nhiều. Ok luôn các bạn ơi. Các bạn thấy như nào nhỉ? Chiều cái tiền đâu mua được chịu rồi Nam anh em rồi là cấp anh chỉ là mong chân của anh Nam thôi. Này nó trượt cái bóng này. Sao bánh nhá? Đi từ đi được 8 bánh em. Ô. Chứ không phải nó sạc thì sao? Không nói không sạc được, nó có 2 đầu mà. Đây là cô. Bảy mấy cái sạc này? 9 cái sạc à? Chiến anh đưa kênh bé. Này trước lưng. Vâng là mới bật lại. Em ơi, đã đi về rồi.
Chốt còn mấy lần. Em lại. Không ý thì anh làm ấy thôi. Ý là kêu được mà có tiền.
Nam lấy ba video. Anh Nam ngày lấy hai mấy video. Vinh ơi, Vinh, qua quay 6 tập, quay 4 tập. Hôm nay cố quay 20 tập nhé.
Cái đó không phải app.
Anh cài app không?
Cái đó chứ. Không ngủ luôn gì hết. Tầm này ai đi đâu mà ngủ luôn em. Cái app đi. Đâu?
Nhưng mà bây giờ em đặt thì anh cũng nhận được.
Tôi muốn.
Được luôn. Em đặt anh đi ra món mát kia đâu.
Đi. Đắt. Đi tí được. Đắt đi. Gọi mấy chục. Xếp vào bên phía đi. Anh xin này em. Thì cũng có cái mưa đêm này thì ấy để bài tờ mai lại sạch.
Anh ơi, em hỏi bạn.
Bạn đi xe một khoảng chơi xe máy. Anh kể này. Anh lấy không? Gọi cái xe máy.
Việt Nam luôn.
Là mua vé 9 của anh lùn
Bếp 34 rồi. Em 34.
Dạ, em là
Không em à?
chạy dịch vụ có con này con bên năm giờ đăng ký chạy dịch vụ chứ nó không đưa được không đâu. Không có cái 8 mấy đồ cái thứ hết rồi. Chết rồi. Xe máy đâu.
Anh biết bọn nghe máy làm gì không?
không nghe máy được không?
Cắt luôn. Hỏi chuyến hôm trước em gọi anh Nam nghe máy.
Đấy, đúng ra dáng được lớn chết rồi đấy. Nó bắt được đâu. Này. Này, con này.
Như này lại phải cống nạp bao nhiêu thì mới được chạy này?
4 triệu, hơn 4 triệu. Đúng là phải nạp 10 triệu cho lên xe về nhưng mà nó trước 4 triệu. Còn 6 triệu lại cái này thì trăm nghìn cho phí chạy phí. Phải đúng 10 triệu là sao? Cọc xe.
Không có 10 triệu. Thế lúc anh trả thì bao nhiêu?
Sợ trả.
Lúc anh không lấy xe nữa.
Ý là cọc xe để mình lấy xe phải chạy phụ này. Không mua đâu. Làm đâu thì không mua đâu.
Thì đến lúc mà anh trả xe nó nói.
Trả xe thì mình báo nó nghỉ. Bây giờ nó phải sử dụng sao
là nó sẽ lấy
đi không mình báo nghỉ với công ty đúng không? Là mình báo nghỉ trong 1 tháng thì mình làm đủ 1 tháng đấy mình nghỉ là xong rồi 45 ngày sau là ví dụ thời điểm mình báo ví dụ nay là 30 tháng 9 đúng không? Mình làm đến cuối tháng 10 mình nghỉ là giữa tháng 11 nó đã là 10 triệu đấy. Nếu mà xe mình không là sai thì nó chỉ gì đâu. Ví dụ như mình đâm độ ốc thì ấy thôi. Trước khi nhận xe thì mình xe nào đi làm ấy lại cái
có gọi thợ xe
máy móc thì cần quan trọng là của ông kêu qua nhận xe hợp xe ra nó bốc người nhiều gọi cứ bảo xong số lắp vào cái số thôi đừng nhận xe này nữa tắt lại nữa.
Throttle body, self-learning.
Khi không đạt không lắp nhất ngang nhất dọc
Dẹp xe đi làm. Xin chào các bạn.